So welcome everybody to today's seminar. Today's speaker is Eva Silverstein from Stanford University, who needs no introduction to this audience. And she will be telling us about de Sitter in M theory and some recent results on that. So over to Eva.
Thank you very much. I am for the introduction and the invitation, and I hope you all stay well and get through this wave. So yes, I'll talk about a very recent paper with Bruno De Luca and Gonzalo Taroba on compactifications of M theory on hyperbolic space. Okay. Now I'm having trouble getting the slides to go forward. Sorry, it's freezing on this end. Oh, there it is. Okay, this is a typical collaboration meeting. Of the 3 or 4 of us, we make a little bit use of an AI collaborator at some point. Okay, so as everybody knows, the positive cosmological constant was discovered now over 20 years ago, and yet it remains pretty mysterious. People talk about the mystery of dark energy, but it's kind of funny because this means rather different things to different researchers. One major goal is to formulate it fully in quantum gravity, which I'll take to mean string or M theory, the connected theory of quantum gravity that has various perturbative string limits and other limits. And this, of course, isn't news. It was discovered 20 years ago, and it led almost immediately to a variety of weakly coupled de Sitter and inflation models over the years, with observationally testable model dependent signatures in various cases. And this is even kind of back reacted on early universe cosmology and observational data analysis, helping it to become more systematic. So we discovered various mechanisms and signatures that from string theory that hadn't been considered from the bottom up and now form part of the sort of standard benchmarks of observational early universe cosmology. And there's, I would say, a concrete start on the upgrade of ADS-CFT, the gauge gravity duality, to the de Sitter case. If I get there today, I'll say a little bit more about that. But obviously, there's much more to learn about this subject. And one of the ways that we can progress is to formulate de Sitter in more generic ways and ideally also simpler ways. So in this talk, I'm going to present a mechanism for de Sitter coming from compactifications of 11-dimensional supergravity, which is to say M theory in its UV completion, which is connected to the rest of string theory, but will be in this limit and work on a finite volume hyperbolic space addressed by various field configurations internally. And it's Casimir energy, which is automatically generated at the quantum level, along with one stress energy ingredient, 7-form flux, yields a stabilization mechanism that's immediate for the volume with positive cosmological constant. And other directions are highly constrained by the famous Mustel rigidity of negatively curved space and effects from the warped product structure of compactifications that also lead to positive contributions to the Hessian, so stabilizing effects. And then if I get there, I'll make some remarks on applications. Okay, so
just a quick question:
yes.
The hyperbolic space, is it compact or non-compact?
It's going to be compact. Actually, it's going to involve a kind of Dane-filled cusp, which the cusp geometry by itself is finite volume but not compact. However, it is useful to compactify that via a kind of higher dimensional analog of Dane filling that Anderson, the mathematician Anderson, formulated. So ultimately, it will be compact, but finite volume is the first requirements to have a finite Planck's mass in 4 dimensions, a finite Newton constant.
Thank you.
Great, thanks for the question, and everyone should chime in whenever, of course. Okay, so what's the motivation for the negative curvature of the internal dimensions? Well, it's among compact manifolds, it's much more generic than otherwise. You can already see that in dimension 2, where you're familiar with a sphere, a torus, and an infinite sequence of higher genus Riemann surfaces, and that pattern continues in higher dimensions. If you think about higher dimensional string theory and reduce to 4 dimensions schematically first, we'll do it properly shortly. But schematically, what you do is you take the higher dimensional Lagrangian, which includes curvature. It includes generically a positive potential or term at leading order that is proportional to the dimensionality, the nominal total dimensionality minus the critical dimension. So generic regimes of string theory actually have a supercritical dimensionality, and also if there's a geometrical interpretation of the extra dimensions, it has generically negative curvature, and both of those contribute positive potential energy as you reduce to 4 dimensions. So there's been a lot of attention to critical dimension in string theory and zero curvature, so Ricci flat manifolds. But I don't see a real reason for that. And instead, the theory generically lives out here in this sort of plot. What we'll do is we'll work. Yes.
Yeah, so this potential V4D that you've written is the potential of the dilaton or all the string fields. What is this a function of?
Yeah, in general, this is of course quite schematic. It's a functional of if you're in a perturbative string theory limit, as you would be with this term being relevant, it's a function of the dilaton and the metric and everything else. Axions.
All fields that are
right. And in fact, this is schematic in a number of ways. And first of all, I haven't indicated all those dependencies here yet, right? But I'm just focusing on the signs, and indeed, you should think of them as a scalar potential, right?
Okay.
Positive to leading order. But there's another aspect of it that's going to be important, which is how you really get a properly defined off-shell effective potential. And this is a problem that was solved in a paper of Mike Douglas's that we'll get to, where you solve the constraint of GR, in 40, the internal part of the constraint, and plug that in to the higher dimensional action essentially, and then you get a properly defined effective potential, and that brings in effects of the warp factor in front of the 4-dimensional part of the metric. So there's a lot more to defining the proper effective potential. So this is right now just sort of schematic and motivational, just saying that the generic choices of these discrete parameters, topologies, and even dimensionalities generically lead you to something with a leading classical positive potential. Despite the fixation in the field, often in d = 10 flat manifolds. So in this talk we'll be in specifically in M theory limit in 11 dimensions, but doing the more generic case of negative curvature.
Sorry, I had a quick question. So you said that you'll be going off shell. So is it intuitively the reason for that? Is it the following, that if you were on shell, then flux compactifications would necessarily take you away from Ricci flatness, and you would not want to do that?
Well, again, so Ricci flatness is a special choice that is not forced on you in the presence of any stress energy, even this first term or other contributions that, as you say, can come from fluxes, and in this today from Casimir energy, from branes and orientifolds and whatnot. There's no reason or expectation that the thing should be Ricci flat. There's stress energy around. But with that in mind, could you restate your question? Because I'm not sure I addressed what you were asking.
Yeah, I guess what I want to ask is that you would not be imposing equations of motion for the fields since you're going off shell?
Right. We want eventually we do impose the equations of motion, but we want to work with in order to do that properly from a 4D effective theory point of view, without losing anything, we want to make a proper definition of this object that makes sense off shell, so that we can then look for the on-shell solutions. It is also useful to go beyond just metastable vacua and think about inflationary solutions, where ultimately it is a solution with kinetic terms also evolving, but at the level of the potential, you can look for, flat directions and so on. So anyway, the plan is to define this object properly and work with the properly defined off-shell potential, but then to indeed impose, v prime equals 0. It's just, you have to do that with the correct v prime. Does that answer your question?
Well,
Yeah.
I apologize. That crops up another question in my head. Well, if you are going to be doing that, and how would you deal with these swampland constraints?
Oh, those are not constraints. Those are, so people have raised these quote unquote conjectures and then treated them as constraints, when in fact, they are not consistent with what is already known in the literature. So the real question is the reverse of what you asked. Why is there this internet sensation of papers repeating purported constraints based on conjectures which did not fully address the previous literature on de Sitter models and inflationary models?
Oh, I see. So in other words, you would not be requiring v prime to be of the order of v?
No, that is not a constraint in the theory.
Okay.
So yeah,
Okay,
people
all right.
repeat those statements, but they are not correct.
Wow. Okay. All right.
Yeah, I
thank
mean,
you.
it's a very weird thing. I can understand why it would be quite puzzling, but I think theoretical physicists are not immune from, kind of perpetuating a narrative. And as far as I can tell, that's what's been happening. It's good to look critically at everything, but there's not been an analysis in the literature that addresses the existing de Sitter and inflation models in a complete or accurate way. So there are already, before this paper, examples of de Sitter models where the ingredients are quite explicit. That goes back to 20 years ago with the supercritical models. It's in the case of the KKLT models, the ingredients are perfectly consistent. The famous anti-brain contributes positively to the potential, as KKLT said, even though these so-called swampland papers refer to studies that claim otherwise, that claim it contributes negatively. So it's a real mess. I mean, I don't know what to tell you except don't believe everything you read on the internet. I mean, these de Sitter models are complicated, and so there's some, the best way to say it is there's some hope that there's something wrong with all of them anyway, and that there's some universal predictions from string theory of the sort that you just summarized. But bear in mind that is a very, very non-conservative perspective. In other words, even without making such a grand claim, there already are classes of well-motivated models of both de Sitter and inflation that hang together, and some of which are even testable using early universe data, as I was mentioning here. And that interaction with observation is a beautiful thing in itself. It's going to allow us to distinguish different kinds of behaviors in a very concrete way. And that includes the famous B modes that will either support or falsify large field inflationary models such as axion, monodromy inflation, and others. And it will also discriminate between mechanisms for inflation that generate significant non-Gaussianities of various shapes or don't. So this is all happening without some grand overall, very strong quote unquote constraint from string theory. So it's not all or nothing, but I want to stress that, the point of view that I'm describing here is really the conservative one, as opposed to a point of view in which you basically dismiss all of this previous experience on de Sitter and inflationary model building, and kind of grandly conjecture that there are really strong constraints and really strong predictions from the theory. That would be, of course, if it were true, it would be a very, very different situation. And maybe these are complicated models. Maybe there's room for them all to fail in some somewhat subtle way, but there's no such thing as a constraint of that sort from the theory as we understand it.
Okay, thank you very much.
Yeah, thanks for the question. Okay. Okay, so given that that's my point of view, why am I even doing this? You might ask, since I was going on about how we have known about the CC for 20 years and worked on it at this level for almost that time. And well, the answer is, I think it would be nice to do it much more systematically and more generically. And it is kind of ironic that going into these limits actually gives us sort of simplification. And we'll see that a bit today. In the case of large D, you get lots of axions. It's like a large flavor type of setup. So sometimes when you add a lot of degrees of freedom, you get some simplifications in the analysis. And for negative curvature, there's mathematical results on relative rigidity of those spaces. So they don't have moduli, and their metric deformations are largely positive when you think about the integrated curvature. And the conformal factor, which is at that level negative, is actually turned around by the warp factor, as Douglas showed. So there's a lot of positive contributions to the physics from these limits. And another thing I'll say just by way of general motivation is what we see in nature thus far is lots and lots of evidence for positive potential energy, constraints on low energy supersymmetry. And at this, without overthinking it, these leading terms in the string theory potential fit with that just at the qualitative level. They do not preserve supersymmetry below the KK scale, but they don't need to, according to at least current constraints on superpartners. And they give positive potential. The theory wants positive potential energy unless you choose to turn these things and many others off. Okay, so that's motivation. So let me build up to the results, starting with the basic, more technical motivation for this particular setup. So here, as I said, we're going to start from a hyperbolic space that it can be understood as coming from a projection of the non-compact hyperbolic 7-dimensional space. We include 7-form flux, and Casimir energy is automatically generated quantum mechanically. So you can sort of count the ingredients here as you like, sort of two-ish ingredients plus an automatically generated Casimir energy. Although the curvature, as I say, the topologies that require some negative curvature are generic. So in some sense, that's not even a choice. Anyway, it's these are the contributions that will enter. And as I alluded to a moment ago, there's a mathematical result called Mustel Rigidity that shows that for any dimension n greater than 2 for a hyperbolic space that is finite volume, there's no flat directions. And this is distinct from the case of a Riemann surface or a Clabbiau. Those have moduli spaces that are dead flat at the classical level. And we'll say more about that a bit later, but aside from the conformal factor, geometrically, metric deformations are not only not flat, but they go up. So there's a positive Hessian starting from the hyperbolic space.
So isn't the volume itself a modulus? Here?
Absolutely, and we're getting perfect. So we're about there now. So let's start with the volume, because for exactly what the reason you said, the volume.
Sorry, I apologize.
I mean, excuse me. It's not a modulus. It's not that it's flat, but it's classically a runaway. Okay, so if what you do is you compactify on the 7 manifold, then the classical term that you get by reducing the curvature term in 11 dimensions is this term. The curvature is in units of the curvature radius 42, and it's positive, and you go to Einstein frame in 4 dimensions, and you get just from this you would get not a modulus, but in some sense something worse, which is a runaway. Okay, by itself it's a runaway, but it's positive, and if you include other contributions, then the potential will take some more interesting shape than just the runaway. And here what I plotted, I should have said, is a function of 1 over this volume, or 1 over the size L here. The potential in the direction of again the volume, it has this runaway piece from the leading classical positive piece from the dimensional reduction. It has also a positive contribution from flux that scales like the inverse volume squared relative to the curvature, as in this term. The curvature scales like 1 over sizes squared. The flux scales like flux quantum squared over length scale to the, or volume squared, so length scale here to the 14th. And so as has been understood since the beginning of the subject, in order to get de Sitter et al., the potential always goes to 0 at weak coupling or large radius. So to get de Sitter et al., it needs a kind of metastable structure. And so in particular, in this kind of expansion in 1 over L, it requires some contribution that is in the middle of these 2 terms I already listed, and is negative. And Casimir energy in this dimensionality fits that bill. So it's negative with the appropriate understanding of the way that spins work on these spaces, and it scales like 1 over like an energy density that scales 1 over like 1 over the length to the total dimensionality of space-time, which here is 11. So the point about the overall volume that motivated this whole project was indeed that these contributions are enough to produce this qualitative behavior that is needed.
So L here is the string length.
No, L here
is the volume, right? The volume of the Calabi also. That is U0.
Okay. Sorry, say that one more time, please.
So your volume that you are computing of the Calabi, that is U0 of L, right? This is.
So this is not a Calabi-Yau, it's a hyperbolic space.
Oh, okay.
It's not.
So
Yeah, it's not a Calabi-Yau, but it has a curvature scale that I'm calling L.
yeah.
It has a we're in 11 dimensions, so the 11-dimensional Planck length I'll call L11, and here I've written things in terms of the curvature radius L in units of L11. That's the L hat, and the total volume is some number that I've just called little v7 times the curvature radius to the 7th power, right? And the 4-dimensional Planck scale is the dimensional the volume over L11 to the 9th from the reduction of the curvature term.
Effective volume of the fold.
Sorry, could you say that again?
Means what is you are defining this U0L is the thing that you are computing.
Yes.
What is that quantity? That is the volume of the 40.
Oh, this is the potential energy. Okay, so
oh, okay.
Yeah, so we're reducing, yeah, sorry, I did call it U here. So we're reducing a higher dimensional gravity theory to 4 dimensions. We have a curvature term in the higher dimensional theory. We have other terms. Say the curvature term, it reduces by integration over the internal space to a term in the 4-dimensional effective potential And, I should say this is still at the same schematic level as I wrote up here. There are other terms for warping and whatnot, but for now, this is strongly motivational because it shows that we have the right structure to stabilize the volume because of these three terms. When we first wrote de Sitter models in the supercritical theory, we noticed that we needed such a negative term in there. It was provided by orientifold planes. And in all subsequent models, it's basically in some direction or other provided by orientifold planes. So that's another type of source of negative energy. Here, we're getting it from Casimir energy. But yes, the quantity here is the four-dimensional effective potential as a function of the volume or the inverse volume.
Thank you.
Sorry,
Yeah,
I had a quick question again. I think mathematicians have studied people like I think Crowley and friends. They have studied I think hyperbolic spaces supporting G2 structures. So is there any is there a possibility that this HN locally looks like probably a 7 torus, and an appropriate orbifold of that would probably produce, at least locally, one of these G2 holonomy manifolds of Dominic Joyce?
Well, I think globally that might be difficult because it's not
They
There
are
are
not
constraints on-
Ricci flat. They're not Ricci flat. I mean,
Yeah,
your
this is-
examples are.
I know, but I'm talking about locally. Locally, is that possible? So I guess what I'm trying to ask is gamma freely acting, or does it have fixed points?
right. So it's freely acting to produce a manifold.
Oh, okay. In that case.
Often when one gets to that, starting from some quote unquote orbifold or even just a hyperbolic polygon, and then takes covers to get the manifold structure. But yeah, ultimately this gamma acts freely.
Okay, all right.
It's a beautiful subject. So in our paper, we reference kind of the standard textbooks on the subject, which are pretty accessible. And one of the motivations here also is the beautiful connections one has between, math and the physics of string compactifications. And so I think that sort of study extends to these hyperbolic geometry, which is a very well developed thing in mathematics. But yeah, I don't know of any connection to G2, as was said. These don't preserve a spinner, and they don't need to because we don't see super partners in nature, and the theory doesn't require it either. So great. Any other? This is great to have discussion. Okay, so let me say just a little bit more about the Casimir energy contribution. It's important here. Well, first of all, others, including us at some points, compactifications on Riemann surfaces, and others have studied internal negative curvature directions in one way or another. And Casimir energy has also played a role in some interesting works, stabilizing various geometries. But I think this is the first instance where we've found it to, where it's played this key role in stabilizing the extra dimensions in a complete compactification scenario. So here's a little bit more about the stress energy that you get from the automatically generated Casimir energy. If you have a system, a geometry with a slowly varying circle of size r, then you can obtain, the stress energy at the leading non-trivial level by taking the expectation value of the stress energy, which is a derivatives of a 2-point function of the quantum fields in the problem. And you can find a nice review of how this is calculated in this older paper. And you get various components that you calculate, and they all scale, as I said, like some constant over the size of the small circle to the total dimensionality, to a power that's the total dimensionality of the space. Okay, so that's a little bit more about the form of the Casimir stress energy, which goes into the equations of motion that we studied. Okay, so it's dominated because it goes like 1 over the size r of the circle to the
Sorry,
11th
hi,
power.
can I ask a question? So the choice of gamma, is it any discrete subgroup of the isometric group which acts freely, or how do we?
Well, it can't be any in the sense that it needs to give us a finite volume space.
Okay.
So there are, known examples, known constructions, a lot of theorems about it. We found in the course of this work a very nice and accessible paper that I'll mention a little bit later by an Italian group that built these, built some useful examples out of. I mean, in general, you can think of these things as obtained by gluing hyperbolic polytopes, and there's a particularly simple construction based on gluing certain right-angled polytopes, and so you can get your hands on explicit examples of this gamma. But yeah, not any gamma would work. So because it has to be non-trivial enough to render the resulting projected space finite volume.
Okay. So gamma is the one relates the two. I mean, you have two independent scales, this curvature scale and the volume, and it's the gamma which fixes the ratio. I mean, this I guess Mustel rigidity.
Yeah, you can think of it that way, right? So I had this kind of fudge factor here, this little v between just the scaling of the volume, which is going to be size to the 7th, and that, like with this, this aspect is very similar to Riemann surfaces, right? Indeed, there is a factor there. It doesn't. It depends on gamma, but not on the curvature radius. So yeah, exactly.
Thanks.
Great, thanks. Okay, where are we? So my computer's a little slow. Oh, there we go. Okay. Whoops. Sorry. I just have to be patient, wait for the time delay on my end. Okay, so to say a little bit more about the Casimir contribution related to the small circles. So one piece of the geometry of typical finite volume hyperbolic spaces is that they have regions that are cusps, meaning they have a local metric that looks very simply like this. This is, if you like, a Euclidean version of a Poincare slicing of ADS with compact cross-sectional torus. So I think everyone will recognize this as a piece of negatively curved space. And it kind of emanates from a more intricate manifold in some region of this, let's call it radial coordinate y. Now, another beautiful contribution to the math literature is that the famous Dane filling of cusps extends to higher dimensions in a paper that a mathematician, Anderson, wrote, preserving the Einstein structure of the space. In such a filling, the cusp doesn't actually go on forever in this y direction. Notice that this is an example of getting finite volume without it being compact if y did go off to infinity here, right? You integrate the volume here and you get something finite, but not compact as y goes to infinity. However, if you fill this cusp in a manner that basically gloms on a Euclidean ADS black hole where one cycle shrinks smoothly and you get a kind of cigar and the rest of the torus stays finite, then you get a compact thing where there's a minimal size of the cross-sectional T6 in proper, in terms of the proper size. So that minimal size is interesting here because it's what dominates in the Casimir energy, which scales like 1 over the size of short small circles, to the 11th power. Okay, so that's why these regions of the manifold are important. And one can obtain a less schematic result for the way that the Casimir contribution to the potential depends on quantities like the cross-sectional volume of the T6 at the end, divided by the size lambda c, let's call it, of the smallest co-moving circle, times the number of cuts divided by this V7 parameter, and the ratio of the curvature radius to the size L of the smallest cycle. There are, in other words, some factors multiplying the 1 over L11th that I highlighted earlier. And I'll say a bit more about that. So that's the Casimir contribution. The flux contribution is here, 7-form flux. Its equation of motion takes this form. In terms of a warp factor U, one can write a specific expression for its lowest energy solution. But as I wrote above it, it basically scales like the flux quantum squared over the volume, the 7 volume squared. Okay, so I was schematic so far about this effective potential. Now we display for you the properly defined 4-dimensional effective potential. This is due to a paper of Mike Douglas's in 2009. It may be my favorite landscape paper because it's a beautiful kind of model independent construction of this object, which applies then, universally.
Sorry, I have a knife question actually
yes.
about the Casimir energy. So
Yes.
Is there some control limit in which we can trust this computation? It's
yes.
useful.
Right. So it requires. I'm trying to get back up there. Don't worry. Okay. Okay. Yeah. So it requires slow variation of the circle in some sense. In other words, you can imagine it's super easy to compute if you just have a circle, right? Or, a flat torus. And that's the calculation that I'm listing here that involves simply this 2-point Green's function with derivatives and taking into account paths that go around the circle, right? And what's required is that the circle be slowly varying in an appropriate sense. And that is true in our situation. So if you look at the paper,
no, actually, my question was about this dependence on this L by L11. So we simply a power here. I mean, so is it some assumption that this ratio is small, or L by L should be much smaller than L11, then we can trust it, or there's some kind of assumption of
oh
this
no,
kind?
no, well, in general we want L much bigger than L11. So right. So actually I'm going to get there, but this is not a complete expression for the potential. So I'll explain how it is that one gets not just the right shape, but what you're asking, which is quite the right thing to ask, which is how does this L hat get to be large radius is what we want.
Yeah.
So yeah, no, that's very important. So I'm glad you asked. But we're not quite there yet, because I would like to address that in the context of the properly defined effective potential, and then is that
Okay, sure.
Okay, great. Okay, so here's the 4-dimensional effective potential that you get when you do the following thing. You take into account that even if you're looking for a maximally symmetric 4-dimensional solution, such as R seeking a DS4 solution, the general metric will have a warped product structure where there's a warp factor. We call it e to the 2a, or u, which is defined as e to the 2a of y. Sometimes one or the other version of the variable is useful. Anyway, there's this warp factor in front of the 4-dimensional metric that depends on where you are in the internal space. And in the internal space, we can basically separate out the hyperbolic metric plus deformations from an overall conformal factor of the internal space. But in particular, this warped product structure, which is very standard, leads in combination with the constraints of GR to a specific formula for the off-shell effective potential that actually makes sense, that's well defined, that is consistent with the constraints of GR. And here's how that goes. So one can process let's say here, the 11-dimensional equations of motion and the 11-dimensional action in the following order, where you impose the constraint equation, meaning you vary with respect to this u, because that includes the Hamiltonian constraint that must be applied, and you impose the internal component of that. So if you like everything but the zero mode of the GR constraint from varying this warp factor, you impose at the start, leaving only the zero mode of it behind because that zero mode part of it is part of the four-dimensional effective theory.
So the
Okay, so-
YI, sorry. So the YIYZ, those describe the internal space, right?
Yeah, these exactly. So
So
this
for
is the
each
internal.
I, so for each value of I, we have a cast. Is that what you meant when you said that number of cast NC in your earlier this schematic?
So I indexes the coordinates. The number of
Yeah.
cusps depends on the gamma. It depends on the manifold.
So how many
and-
non-contractible cycles?
Yeah, that
Yeah,
also
how-
depends. I mean, that, the things about the homology depend on gamma, right?
Oh, okay.
Yeah, there are beautiful theorems about it, by the way, that the fundamental group grows exponentially for any hyperbolic manifold. So there's a lot known about it, and in any particular example, you can compute those things. So for example, the ones we refer to by this Italian group makes computations of all the homology elements among other quantities. So one thing that is true of those models as well, which is useful for us, is that the volume in the cusps and the volume away from the cusps, defined in a certain natural way, are comparable. They're not, there's no big hierarchy between the two. So that'll come up a bit later. But here what I'm trying to quickly summarize is how you get to this proper formula for the effective potential. And what you do is you impose the GR constraint, which you can view as an equation of motion for the warp factor U from varying with respect to U. And then plugging that solution to the constraints, which is now a functional of the other metric variations, the ones in here, plugging that back into the action and reducing to 4 dimensions. And that's what basically gives you this formula. So this formula is sprinkled with warping dependencies. This U appears in this formula, and this U is evaluated on the solution of the constraint. And so the U in this formula is a functional of the metric, the internal metric, the H and the B in this presentation. Furthermore, the constraint, as Mike pointed out in this old paper, in 4 dimensions takes a very nice simple form. Before we reduce to the solution for the flexion, just think of it as some floating constant value or U independent value. This is just like a Schrodinger problem. So it's particularly if this C, which I'll explain shortly, if that is small, it's like a Schrodinger problem at 0 energy with a particular effective Schrodinger potential. This C is actually the leftover piece of the 4-dimensional constraint, in the sense that it's a constant that we haven't yet fixed. And if you do everything I just said, which is to say you solve the constraint equation for U in this form, plug it back in and so on, then you find that the effective potential takes this very simple form, with C being nothing but the 4-dimensional curvature of the 4-dimensional component. G Newton, 1 over G Newton, I should have written here. Let me do that now, if I can. Well, I'm not sure I can. So 1 over G Newton is this integral here, this integral root G7U. So anyway, there's a way of processing the Einstein equations, imposing the constraint from the start internally, plugging that back in before doing this reduction to 4 dimensions, and therefore giving a well-defined 4-dimensional effective potential that's a functional only of the internal fields. So that's the punchline of this slide and this paper. And the form of the constraint equation is really quite illuminating because it teaches you a lot about the behavior of this function u that enters into this formula as this overall u squared here from the determinant factor, and also in this offset in the curvature term. Okay,
Sorry,
so
can I ask
yes.
one question? The fluxes, I mean, the F7 flux is not stabilized. Is there nothing to stabilize it because there's no modulus here?
Well, the F7 flux has a certain solution that I just flashed here. It is sometimes useful to, since this is an off-shell potential, it's sometimes useful to leave the flux as a constant for purposes of getting intuition from the Schrodinger problem here. But when we solve the equations, it's just the flux is replaced by this solution of the corresponding axion equation of motion, or the form field equation of motion. Is that what you were asking?
Yeah, I guess so. Yeah. So I mean, it's something which you can dial up or down. I mean, there's nothing.
Oh yes, that's an important point. So I already kind of alluded to it probably too quickly. There's a flux quantum number, so it's quantized, and there's this integer n7, and it can be dialed quite finely because you know, this 1 over volume to the 7th, or equivalently 1 over L to the 14th power, that is competing with these other terms like the curvature term, which scales like 1 over L squared. And so by shifting the flux quantum number by 1, you actually get quite fine, Buzo and Polchinski called this a discretum. You get very fine variations, discrete but very fine variations of the flux squared term, indeed. So the parameter is discrete, this n7, but it always comes with this 1 over volume factor. So it's
and I guess probably a related question is that because of this this Mustel rigidity that you mentioned, does that imply that essentially the cohomology complex is trivial, and therefore you don't have any modulus appearing anywhere in the potential?
Well, you do have metric variations. It's not that we can declare full understanding just from the lack of moduli, but what that is saying, it is important. As you're suggesting, it's saying, you know, that that as you move away from a solution, let's say just at the level of the mathematical statement, both Mustel rigidity and the corresponding statement about, you know, sort of differential geometry, is saying that this term integrated against the det g square root, this integrated curvature term has no flat directions, and so as you move away from the Einstein metric, you go up or down, right? I mean, you at the quadratic level, if not at the linear level. And then, you know, you have to ask, okay, which way do you go? Do you tend to, you know, do these metric variations take you off in a negative direction, like a so-called tachyon, or are they stable? Do they take you up in the effective potential? Okay, so and what I was saying before is that almost all of them take you up. The ones that take you down are conformal factor variations. So there's a standard thing about gravity, which is that conformal factor has negative net contributions to the gradient terms. And that's true in such a compactification. However, and I'll get there shortly, but basically that is true regardless. Whatever compactification you would do, you would have such a deformation of high momentum modes of this B that at the level of the integrated curvature looks like a hopelessly negative direction. But the reason that doesn't determine the fate of compactifications is because the warp factor, when you properly solve the equations of motion, including in particular this constraint, the corresponding effective potential does not have such a downward direction, even though this piece would. So the warping is not only, you know, important to include for completeness, it really plays an important physical role in the consistency and stability of the theory. So
so essentially these deformations Hij, my guess would be that essentially you'd be looking at some perturbation of the, let's call it the Einstein equation in the presence of fluxes, and go first order, et cetera, and solve them for the perturbations. Is that right? Eventually, that's how you'll be solving. You'll be probably getting some coupled partial differential equations for H by looking at
correct.
perturbation.
That's right. That's correct.
Okay, so I mean that's what. So I mean the reason you're calling this whole thing off shell is because you're looking at perturbations of about the on shellness.
well, it's just that
Dumb question. I apologize, but I'm a little confused there.
well, so I'm saying on shell in contrast to the naive thing you might do without solving the constraint. I'm saying this potential can be used off shell. It's a formula that makes sense even if you haven't yet solved the equations of motion.
Okay.
And I'm just saying it even though what you want to do is solve the equations of motion. Whereas otherwise it wouldn't have. It would. I'm just saying. I mean, this is kind of a long-winded way of saying one should solve the constraints of GR. And the point of this Douglas paper is that when you do that, the effective potential acquires extra dependencies, which are important.
Okay, thank you.
Maybe you have already said it, but I didn't get. So is it true that even off shell, there would not be any flat direction or tachyonic direction for the metric and other things?
Yeah, there would not be flat direction for the metric. So the mathematical statement about the hyperbolic spaces and similar Einstein spaces is that there aren't flat directions. Furthermore, basically you do some decomposition. Basically, the H directions are positive. The B directions here, for gradients of B, naively look negative. However, when you actually write down the effective potential that includes the warping effects, that apparent negative direction of the conformal factor is not present. The warping effects net turn that around as well. Okay, so
yes, I understand that, but so this conformal factor is the only potential part of worry. But I didn't get what you said, that is not a problem only on shell when U is on shell, or is also true off shell. This is what I didn't get.
Well, you needs to be on shell. Thanks for the formulating your question in that way. Let me make it really clear. U needs to solve this equation because that's a constraint equation, right? So when I say off shell, I'm not saying U gets to be off shell. I'm saying U must solve its constraint equation. So this U sub C means U solving the constraint equation. And once U solves the constraint equation, it's a functional of just the internal variables G7 and C6. I mean, that's another way of saying what we mean by off-shell potential. It's not, what we mean is we want it to be an off-shell potential that depends only on the internal degrees of freedom, the things that are scalar fields from the four-dimensional point of view, whose potential energy we're interested in. So I'm not saying you work off shell in U. I'm saying that throughout your study of the deformations of this potential, of this metric, this internal metric, you solve the constraint for U. So the effective potential depends on these directions via not just terms like this R7 and the F7 squared and whatnot, but also through U. Is that clear?
Yeah, thank you.
Yeah, no, thanks a lot for the questions. This is perfect. Okay. So I was saying that this constraint equation is similar to an effective Schrodinger problem, and with an effective Schrodinger potential of this form that's related to the naive dimensionally reduced potential. And one thing to say about that is the signs are such that the warp factor here in this analogy plays the role of a wave function. And if you have a wave function in a system with some potential energy, and if the potential energy becomes very positive, the wave function dies below the barrier, the potential barrier. And the way the signs work out is that the negative four-dimensional energy contributes positively to this potential. So things like a Casimir energy that might blow up as a circle shrinks all the way to zero results in a screening effect by you, the wave function. So, and I was saying just in words previously that when you take a internal space and you rescale it by a conformal factor, you find what looks like from the naive expression, the integral of the curvature, a contribution which looks, terribly negative. This is a standard thing about the conformal factor in gravity. And here what it does is it leads to a contribution that is quadratic because of the rigidity, but it's in the absence of moduli, but it's negative. However, when you plug back in the correct solution to the constraint, you find that this turns around. So this conclusion is incorrect. And it's a very simple calculation to show that, and kind of conceptually it's related to this point that the constraint equation leads to sort of screening of negative energy by the warp factor when the negative energy gets too strong. Okay, so
Hi,
here let
sorry,
me-
can I ask? Just
Yeah.
the metric in the internal space. I thought rigidity will tell you that it's. I mean, a fundamental group will just determine the metric, right? So the Hij that was there on the previous slide. I mean, yeah. So on the compact hyperbolic space, I thought that once you know the fundamental group, you just know the geometry. Maybe I got confused with.
Well, it's true that if you specify that it's hyperbolic, you know the geometry. It's also true that that is a stationary locus of variations of the curvature term, right? So it's like any Einstein space. So that's why it's natural to think about that as kind of a fiducial geometry dressed up with warp and conformal factors, but some fiducial geometry here then perturbed. But physically you can deform away from the from the maximally symmetric metric, the Einstein metric, and
but the small h is determined by gamma. Is that the right way to understand rigidity? Or I thought that
so the underlying hyperbolic space has a metric that is hyperbolic, and that's what I'm indicating here. So that is already for the hyperbolic space that's determined, and then when we mod by gamma, maintaining the Einstein property, the hyperbolic geometry, we get still the same metric locally. But here what we're doing is we're allowing ourselves to physically deform away from that that constant curvature metric, right?
But the rigidity won't constrain that. I thought.
Oh, it will. It will. It will. It has an implication that there will be some the potential. I mean, the upshot is the potential rises in this direction. Okay.
Okay. Okay. Mm-hmm.
Yeah, but but still, this is a physical deformation.
Okay.
Yeah. So.
I guess one could say that the number of non-vanishing Hijs will be determined by gamma, but the evolution is going to be determined by its equation of motion.
Well, I mean,
I think my confusion was I thought once you know gamma, you just know the maybe that rigidity tells you that you just know the metric, but maybe that was not.
Well, yeah. I mean, rigidity. The mathematicians use the term rigidity, meaning if you insist that it be Einstein, there's no families of Einstein manifolds. In that sense, it's rigid. In physics, what that entails is there's no flat direction, but there could be non-flat directions, right?
Okay, okay, got it.
And yeah, in terms of what the spectrum of these is, that's related to gamma. That gamma introduces boundary conditions and such. That's right.
Okay, thank you.
Great. Okay. Okay. So this is okay. There are very concrete constructions of these hyperbolic spaces. This is a picture that's meant to evoke how things work in our mechanism in sort of general terms. So we have this underlying hyperbolic manifold. It's dressed with warp and conformal factor variations. Those take a kind of shape I've drawn here, and we have some patchwise solutions that illustrate this that I'll flash for you a little bit later. But what you would expect physically is a shape like what I've drawn here. In particular, the B is like the volume, and Casimir energy pushes down on the volume. So when it's operating, you'd expect B to be reduced, and conversely, when it's not operating, you expect a force on B to increase it. And so although there's some average value of the volume, the profile of the conformal factor should look like this internally. And there's a corresponding behavior of the warp factor. One piece of combination of the equations of motion, which is important, is this one, which shows that the combination. So one thing I would like to highlight here is the net curvature contribution in the potential energy. So that in the formula for the effective potential that we dwelt on in the last slide or two, that was not just the curvature minus the curvature, which it's by itself contributes positively, but also there was a contribution to the warping from the warping. So specifically this gradient of the warp factor. Let me just for one moment go back to show you where I'm. So here, so there's this net curvature term here, along with the Casimir energy and the flux. And the warp factor also sits out here just multiplicatively. So this net curvature term is interesting because it includes not just the internal curvature, but also this warping gradient. Okay, so moreover, there's a combination of the equations of motion, which is useful, which is this combination highlighted in this other paper, where that net curvature contribution locally, in our context with our particular sources of Casimir energy and flux, that takes this form. We will throughout work in a regime where we tune these three contributions in the volume stabilization potential so that the four-dimensional Hubble is small, and that corresponds to this C over U term being negligible. So what really matters in this equation are these two terms with the signs that I've indicated. So even though the Casimir energy is negative, what appears here is minus that, or the absolute value of it. And so what you see from this is that this curvature contribution can be positive in the presence of the Casimir energy, but in the regions where the Casimir energy is not dominant, instead it'll be negative. And so there are regions where this curvature term in the potential is negative, regions where it's positive. And that's useful because we can tune those against each other in order to ensure that the curvature and Casimir as well as flux contributions all compete. The Casimir energy is smaller than it's quantum, and so it has a certain suppression that's in the factors of L11 that we've indicated in the formulas, for example, here. And so in order for the three terms to compete with each other, that requires, as in any model, some large number in the problem. And in this context, it's the net contribution of the curvature Okay, so let me maybe say a little bit more about that now. We can formulate some dimensionless variable that represents this tuning, and we have a specific mechanism for it. We can adjust if it's too large or too small by changing some of the discrete parameters that we have available in our system. So for example, if it's too small, we reduce the flux quantum number. If it's too large, we can add volume that doesn't contain Casimir energy, and it's very, very easy to do that given the these gammas that we understand. Okay. So just to give you a picture of a three-dimensional analog of these types of spaces, they're extremely concretely constructed. And as I mentioned earlier, they have comparable volumes in the cusps, which contain Casimir energy, and the non-cusps, which don't. So one has this ability to ensure that we have this small number in the problem that enables the curvature term to be small enough to compete with the Casimir energy. Okay, so this requires for control not just the curvature radius L being large, but also the smallest cycle size being large, and that also occurs once we tune this A to be small. So if we apply our stabilization mechanism, where we balance the curvature and Casimir contributions, with this A in place, we get a large curvature regime. So this is analogous to control parameters in the earlier models of de Sitter, D much bigger than D critical in the supercritical models with Maloney and Schrodinger. W naught in KKLT, the flux quantum number can be small there, so that the classical and non-perturbative contributions can compete, and various topological quantum numbers and in other cases. So this is in this, I think, so I know there was a question earlier indeed about how these can compete consistent with large radius, and that's specifically, where that comes from in our case, namely this tune of A. Sorry, I went to the end necessarily. Okay. Okay, I'm trying to get back to where we were. Okay, so here's a kind of figure summarizing our mechanism. We have this net tuned curvature term that competes with a negative Casimir. Flux is also very variable. The hyperbolic Hessian and also warping effects both go in the direction of positive Hessian, although it would be quite a long exercise to compute the Hessian explicitly. I'll say a bit more about how these positive contributions arise, but it's basically related to the rigidity and the screening effect of the warp factor. Okay, so I'm going a little faster since wow, since it's already over time, I didn't realize. So let me just get to do just a couple more things and then summarize. So, I made these statements about small a, about solutions and the way the profiles of the solutions work and so on. And within these regions that have a simple kind of radial geometry, a torus times a line, basically, where then it gets effectively Dane filled, we can write explicit solutions that realize all those features, that all the sources compete, that the filling cycle shrinks smoothly, and that A is small. So this is kind of a rescaled picture of such a solution. Okay, so now let me just say a few things about the Hessian. The statement in math, which I'm just sort of for fun posting from the classic text on Einstein manifolds, is that if you look at the curvature term, indeed, most of it is positive with negative sectional curvatures. And the part which isn't, the conformal mode part that I was talking about before, by itself would give something negative in the potential. However, when you take A, which is the log of the warp factor U, you solve its equation motion and you plug back in, you find a positive Hessian. So this is the beautiful observation in this paper. we can make a more general, one of the contributions we made in our recent work is to kind of expand on what Douglas showed in that regard by showing that model independently near small cosmological constant, if you decompose the Hessian into parts that came from variations involving U and the warp factor, and parts that instead came from variation of the naive potential with respect to metric variations, collectively called gamma here, you find just after minimal processing using the effective Schrodinger formalism, where U is the wave function, V effective is like the expectation value of a Hamiltonian, you find that there is a universally positive contribution from warping. That goes in the right direction. Using the Schrodinger problem formalism, we can also make use of the trial wave function sort of approach. And there we find a trial wave function, which, at least according to some crude estimates we made, yields apparently positive Hessian. And we find, if we look at modes that are localized near our explicit radial solution, we also find some at least test examples that are consistent with that. But this is not the same as a complete calculation of the Hessian in a full in the exact system. That sort of thing is has only recently been completed for Kerr black holes, for example. So it would be a major undertaking. However, all the indications we have are positive. So positive contributions from the rigidity, positive contributions from the warping that takes care of the conformal factor, and this trial wave function, and also some tests in our explicit solution near the Casimir region. So then if you take this Hessian and you estimate how strong the shifts of any residual tadpoles in those modes H would be, you find they are suppressed. And you can find the analysis in the paper. Finally, there's a very amusing no-go theorem for ADS in a certain range, which is basically a reversal of the Maldacena-Nunez de Sitter no-go that they had when they didn't include so much as the leading term in the potential or any quantum effects or even classical but stringy effects. If you take their sort of approach, but you take into account the quantum Casimir effect, then you find kind of reversing their analysis a regime where you can exclude ADS extrema in such a range. Okay, and then the 7-form flux is generally generalized to something that if you turn on F4 flux contains some axion dependence, and that leads to a standard form of inflation called axion monodromy inflation in this context. Okay, so we're over time and I'm going to stop there. I had more to say about various further analyses of the equations of motion, the PDEs using neural net methods and such, as well as applications to dualities and quantum gravity. But there was a really good discussion of the main topic. So let me just move to the summary. Oops. And leave you with that. I'll be happy to take any further questions.
Thanks a lot, Eva. It was a great talk. So we should have a few more questions then.
I just had a couple of things to ask. This what you defined towards the end as F tilde7 in terms of F7 and F4. Maybe I'm missing something, but isn't that F7 and F4 are just Hodge dual of each other?
No, yeah, it depends which components you're talking about. It's true you can work with one or the other, but if we decide that we're going to work with magnetic components internally, then these are both separately present. So yeah, they are. Okay. They are, but yeah,
And the second and the final question is that can you bypass the ADS-Dogo theorem with the inclusion of these high derivative quadratic corrections in the supergravity action?
Well, I mean, there are plenty of ADS examples that one knows. So the way, in some sense, although, I was saying it's amusing. I'm trying to get back to the page. There it was. The ADS solutions that are known just have a weak, in this language, they would just have a weak Casimir contribution, meaning they're very large radius. They don't have any of these small circles, and they just have basically flux and positive curvature supporting them. That's that's how the Freund-Rubin solutions work. So I'm not trying to imply here that it's hard to get those traditional ADS solutions. But what's amusing here is that if you have a strong enough source here, you can, conversely to the Maldacena-Nunez, in this regime, instead of excluding DS, you actually exclude ADS. But it's not inconsistent with the existence of other regimes, reverse of this, where you have the familiar ADS solutions.
Right. Okay, can I, sorry, with Ian's permission, ask one more question?
Sure.
So at any point in any of the equations, I mean, I'm actually, what I'm about to ask is actually motivated by the following observation, that more than 2 decades ago, Anastasia Volovich had shown that in the context of Witten's MQCD, when looking for supersymmetric 3 cycles in G2 Hanonomy manifolds, you end up with obtaining and solving these Monge-Ampere equations. So do you end up getting those Monge-Ampere equations in the context of hyperbolic spaces while solving for maybe any of the HIJs or something in your calculations?
I'm not sure if we didn't. I'm not sure. I mean, we have particular PDEs here, and I don't. Yeah, I didn't recognize them as Monge-Ampere, but yeah, maybe they are related to some standard named equations. Yeah, sorry, I don't know.
So, I mean, doesn't the Hessian appear anywhere explicitly any of the equations or equations that you solve?
Well, the Hessian is certainly relevant. So let's, sorry, I'm going the wrong way. Well, for example, I went over this quickly. So we have, this hyperbolic space, we have it dressed with the varying conformal and warp factors that follow from the variation, from the localization of the Casimir energy. And then we have, all these metric deformations, most of which are very, very massive. In general, one wants to estimate how far they get shifted from their fiducial value given any residual tadpoles. And so that equation, for example, is given here. Such a shift is the inverse Hessian times whatever tadpole they have. So in other words, basically V prime over M squared, where M squared is their mass squared. I mean, this is one place where the Hessian appears. But yeah, I mean, maybe I'm not quite getting your exact point, but yeah, the Hessian is, the quadratic deformation, and it's in there.
Actually, I have some question about the Hessian, about this Hessian too. So you said that because of the once you put the warp factor on shell and you solve the Schrodinger equation, it becomes positive, whereas otherwise it can have tachyonic directions. So can one understand physically what the wave function is actually doing that allows this to happen?
Yeah, well, so, okay, I should say this original point by Douglas, where what you do is let me just describe this quickly, just a little more so that it sinks in, because it is a very interesting point. So first, if you imagine you didn't have this A and you just deformed by the conformal factor some internal metric, then you would get these terms. This first piece is the new curvature having turned on this varying B. So you integrate that by parts, and then you get this expression, and you can see that if you had no A here, so just kill all the terms with the del A's, then you've got the standard negative del B squared term. And notice that this would be true just for any space. Compactifying a torus doesn't matter. It has nothing to do with the hyperbolic stuff. And so just technically what happens here is, well, we do have A, you solve its equation of motion here, and you plug that back in, and I didn't write all the steps here, but it turns it around to have a positive mass matrix for these short modes of A and B, short modes of B in particular. So at that level, I'm just trying to explain it's just a very simple matter of solving the equation. And from that, you can see, what basically happens is this term would also go the wrong way, but it's this linear term. I'm not giving you a particular physical picture of this calculation and how it turns around, but it's just a true fact that you solve the equation, plug back in, and you get that positivity. The other thing that is more perhaps intuitively appealing is something I pictured earlier somewhere, I think. Yeah, so, well, there's this Schrodinger-like problem. This U is like the effective Schrodinger potential, and it's basically the negative of the naive four-dimensional potential, meaning negative terms like the conformal factor in the effective potential, the naive effective potential, contribute potential barriers here. And so a potential barrier causes the wave function to contract, to die off below the barrier. And so some of the effects of warping can be understood from that die-off effect being like a screening effect of negative contributions. But it's really not just that's going on, it's also this gradient playing a role. So I don't know, that's what I can say. It's not, the technical statement is exactly what you summarize, that you solve for U, plug back in, and you get a proper definition of the potential, and you also find that particular naive instability of the conformal factor is absent.
Yeah, but just maybe a very wild question that if you could understand maybe this, how the wave function is playing a role, could it be conceivable that in some other scenarios also you could do such a thing, like you can lift it up?
Well, I think it's I think it's a really interesting and perhaps underappreciated point. I personally didn't appreciate it enough until this project. So I think that's a great comment. I think it could likely be used more widely. Anytime you solve the equation of motion, this U equation of motion is in there. So in that sense, it's already part of any complete study. But here, it turned out that it was quite useful and also a lot of fun to persist with the effective wave function picture, which is a formal rewriting of the effective potential in terms of this U now as a wave function, and basically carry out standard quantum mechanics perturbation theory to derive some consequences. So just in a nutshell, this sort of derivation, and there's more like it in the paper we wrote, starts from the fiducial geometry and then does standard quantum mechanics perturbation theory to capture the effects of deformations in various metric directions. And that's where one finds, if we expand around small cosmological constant, meaning that the system is essentially in close to a zero energy eigenstate, then you get this universal result of a positive contribution to the Hessian from warping. It's not saying that the rest of it couldn't include negative directions, but it's a universally positive contribution. And we also know that part of the rest of it, the curvature piece, has this positivity. to it. So that's yeah, that's as much as I can say here, but indeed I'm pointing to this because it's perhaps of broader utility than just this specific scenario in that it's model independent in this sense.
That's interesting. Okay, so more questions. We can have one more at least.
So can we like understand it in this way? Can you hear me?
I can barely hear you.
Oh, now can you hear me?
Yes, that's better.
So can we think of it like this fashion, that in the four-dimensional part, the four-dimensional space-time, there we are observing a disputed like expansion of the universe, right? Means with the cosmological constant fixed by this four-dimensional effective potential that you derived.
Right.
That is just kind of the setup. So this warp factor evolution, we can think of it as like how the scale is changing during inflation. Is that?
Yeah, I know what you're saying. I think if you do a time dependent case, then the metric is a little bit more general. It's not literally de Sitter, and so one does a similar procedure, but including the kinetic terms, which are now non-trivial, right? So it's not exactly any of the formulas I wrote, but you can work with this effective potential to find flat directions so that inflation will work.
Okay.
And that's all I really said about the inflationary case, which was this realization of axion inflation.
Okay, thank you.
But yeah,
Okay.
just to be clear, the warp factor variation I was talking about was in the internal, in the y's, if you want, in the spatial directions internally.
Okay, so it is quite late here now, so maybe it's good to wrap up. So thanks, Eva, for this great talk again, and for staying with us, and also for waking up early in the morning. And
No problem. Thanks a lot for the invitation. It was nice to meet you all.
it was a pleasure, and hope you will come to Chennai someday.
Oh, thank you very much. I'd love to.
Okay, so
and
have
vice
a nice.
versa.
Okay, thank you very much. So have a very nice day, and hope we see each other in a better world. And,
Yes. I hope things resolve smoothly in India. I wish the best for all of you there.
Thanks. And,
Okay.
goodbye then. See you later.
Goodbye.
Bye.
Bye.